Hi there. Occasionally I buy strange and non-working devices on eBay for parts, especially if the units are very cheap or look interesting. This device here ticked all of these boxes. The metal enclosure alone with its fetching color scheme would cost way more than what I paid for the whole thing. I get a nice 100 microamp meters as well, and the high voltage label hopefully indicates some interesting things inside. Another part of the fun is trying to figure out what it was meant for originally. The only way to learn more is to open it up, which is always the most exciting part. What will be inside? You are joining me in finding out. There's no guarantees as the listing did not show it open, but it's clearly not empty from the weight alone. Trying to open it after removing the 4 self-tappers on the top, but the housing stays firmly together. Turns out there are 4 more self-tappers on the bottom. It's moving, but something internally is jamming and prevents the cover to give way. After a lot of wiggling, I finally get the cover off. There's a perf board PCB and an interesting looking transformer inside. I can see where the original blue and brown mains cable was cut, and there's a piece of the original earth wire left too. The meter is connected through the red and black wires to the PCB, which clearly contains a full bridge rectifier made of discrete diodes. There's a shunt resistor for the meter in the middle. The AC part of the rectifier has a large series resistor connected with a brown wire to the transformer and a blue wire to the front panel socket. Measuring the resistance of the transformer tabs, judging by the rest of the wiring, the most right ones are probably for mains, and 100 ohms reading sounds about right for 240 volts AC primary. This winding is not connected to any other tab, so it's an isolation transformer, good to know. The secondary winding has a resistance of about 1.5K. That explains the high voltage sign. This is an isolated step-up transformer. To give the transformer a quick test, I stripped the isolation of the cut-off mains wires to be able to connect them temporarily. Driving it through my light bulb current limiter just in case, and with just 50 volts AC for my variac, the output is about 200 volts AC. In other words, this transformer has a 1:4 ratio between primary and secondary. At 240 volts input, it will deliver a cool 1000 volts AC. Nice! The unusual transformer core led me to try powering it with higher frequency AC voltages from a vintage signal generator that has already a very high output voltage. Running the transformer at 400 Hz with 100 volt AC input is no problem, and I get easily 400 volts at 400 Hz out of it. 500 Hz is also no problem. 1 kHz still going strong. 2 kHz and more than 430 volts AC. 5 kHz, which is more than the earning meter on the left can deal with, but the output is now more than 480 volts, very nice. The rise of voltage is probably due to the signal generator. This transformer is definitely very useful, and I decided to move it into its own enclosure as I have other plans for the box it is in now. With the transformer investigated, time to look at the meter. To check its working, it's best to disconnect it by pulling off the spade connectors. It says 100 microamps on the front, and this is exactly what it does when I feed 100 microamps into it. At the same time, I measure the voltage drop across the meter, which is 30.3 millivolts. With these two values, it's easy to calculate that this meter has an internal resistance of about 300 ohms. Now that the meter is disconnected, it's easy to measure the resistance of the shunt resistor that is normally in parallel with the meter, about 150 ohms. And the large series resistor in line with the brown AC wire is 1 megohm. This is what we have established so far, the transformer with its primary winding connected to the switch and the fuse, but then cut off. The full bridge rectifier with a 100 microamp meter and a 150 ohm shunt resistor, One end of the rectifier is connected via a 1 megohm to the high voltage secondary of the transformer, the other to a front panel socket. The 100 microamp meter itself represents a 300 ohm resistance and at full scale of 100 microamps drops about 30 millivolts. As it's wired up, the meter has a 150 ohm resistor in parallel and, ignoring the resistance of the rectifier diodes, a 1 megohm resistor in series. Since we know that at 100 microamps there are 30 millivolts across the meter, this means there are also 30 millivolts across the 150 ohm resistor. Using Ohm's law, volts divided by resistance means a current of 200 microamps flows through the 150 ohm resistor. So the current through the 1 megohm resistor at full scale is 300 microamps. With that, we can establish, again using Ohm's law, resistance times current, to calculate that 300 volts are dropped across the 1 megohm resistor. In other words, what we have here is a voltmeter that will show 300 volts DC at full scale, ignoring the small drop through the forward voltages of the diodes. Putting a DC voltage of about 150 volts onto the brown and blue wires of the meter circuit, and the meter shows exactly half scale, which proves that the calculation is correct. But this circuit is clearly for measuring AC volts, not DC volts. Running the same test, but this time with 150 volts AC, shows a maybe surprising result. The meter is now quite a bit below the half scale mark. To explain this, I have to briefly touch the thorny subject of RMS, or root mean square. I made several videos about this, so I refer you to those for details. The digital meter is showing 150 volts AC RMS. The definition of that for a sinusoidal wave is shown here. Using this formula, the peak amplitude of a sine wave of 150 volts RMS is 212 volts. The meter uses a full bridge rectifier and therefore sees this waveform instead. The DC voltage varies 100 times per second between 0 and Vp. The needle of a mechanical meter can't follow that speed and therefore shows an average. The formula for the average is shown here as well. Using that formula, the 150 volts RMS or 212 volts peak produce an average DC of only 135 volts, which is exactly what the meter shows. At DC, the average is of course the same as the peak. Hence, the readout differs between DC and AC when using apparently the same input voltage. If this were an analog multimeter, the series resistor would usually be tweaked so that 150 volts AC show the same needle deflection as 150 volts DC. That's a convenience feature, trading in true average readout for a fake RMS readout. That tweak works of course only if you measure AC sine waves, because the average values for other waveforms are very different. Therefore, such waveforms will produce wrong readouts and such a meter is not true RMS. The fact that this circuit does not contain such a tweak could mean that the meter was always meant to show true average voltage, for example because whatever circuit or probes it was using resulted in non-sinusoidal waveforms. Then again, given that the transformer produces 1000 volts AC and with a given series resistor, the meter would overload at just 333 volts AC. This probably means there was originally some additional series resistor somewhere, probably in an external probe connected to the front panel, and that might have been selected to show RMS instead of average for sinusoidal waves. In my search for clues about the makers and purpose of this unit, I noticed some handwriting partially under the PCB. I removed the PCB to read it, but all it says is outside only. I would guess it's a note to the guy with a green paintbrush to only cover the outside of the enclosure. A couple of other clues, like proper index holes for the meter and the switch, indicates to me that this is a professional build. Most amateurs, and I include myself, would not bother with such details. Yet the use of perf boards shows it's probably a one-off. I would guess a university or factory building their own specialized test rigs. The front panel socket is not designed for higher voltages, but you could touch the conductor easily if no mating connector was plugged in. I guess that's what the 1 megohm resistor is for. At 1000 volts, that would limit the current to a non-lethal 1 milliamps. Also, it does have two poles, both have been wired together, so clearly there must have been some other high voltage connection. Most likely that was the job of the 3-pin socket at the back. I have seen these mains connectors on old vintage UK equipment from the mid-70s, which might be the date of this unit. It's of course possible that this was indeed the mains power connector and the hole with the comet was used for high voltage, but of the 3 pins, the top pin appears unused. Given the remnants of an earth wire inside, that would count against the 3-pin connector being the mains connection. One could speculate that this might have been some sort of isolation tester or to measure high ohm resistors. If that would be the case, an additional resistor in the probe would be needed to limit the current to 300 microamps if the probes were touching each other. For example, an Rx of 0 ohms. 300 microamps because 200 microamps go through the shunt and 100 microamps through the meter. Such a contraption could measure up to 100 megohm resistors reasonably well. But was that what it was used for? No idea. If anyone recognizes the device, please leave a comment. To end this video, I did extract the transformer and put it into a new plastic housing that you see here. The connections are done using shrouded banana sockets for safety. Here it is all wired up. I'm sure it will prove valuable in the lab. While doing the wiring, I decided to add the original fuse and the fuse holder on the primary side. If you like my videos, don't forget to subscribe. There are many more projects, repairs and reviews coming up, and it would be great if you decided becoming a Patreon. That would really help this channel. Thanks for watching.